Now, if you remember what was happening in the generalized random graph, what we see is that the limiting degree distribution is Poissonian. It has a mixed parameter, so it's a mixed Poisson distribution, but it is a Poisson distribution. And we all know that a Poisson distribution can take on value 0. So that in particular implies that indeed the proportion of vertices with degree 0 in these models is always strictly positive. And likewise, there will always be vertices, in fact a linear number of vertices with degree precisely 1. There will always be a positive proportion of vertices with degree precisely 2. So you will not obtain a graph, for example, with all the degrees being even, or with all the degrees being greater than or equal to 3, or whatever, right? So there's less flexibility in choosing the degree sequence. And the nice thing about the configuration model is that you're very free and very flexible in choosing the degree distribution in order to study precisely what the effect is of the degree distribution on all sorts of properties. For example, on connectivity. Right? I mean, if you have isolated vertices, clearly you're not going to be connected. But if all your degrees are at least 1, will you be connected? Well, probably not. In the configuration model, when you have a positive proportion of vertices that have degree 1, well, you can create very small components by just pairing up 2 vertices of degree 1. And you're going to get a connected component of size 2. Now, if you have order n of vertices with degree 1, okay, this is going to happen a linear number of times. And therefore, the graph will not be connected. Now, what happens when all the degrees are at least 2? A little bit more tricky. There actually turns out that with positive probability, the graph can be connected. But then also with positive probability, it cannot be connected. And in fact, if you look at the giant component, it will be almost everything. N minus a random variable that actually will converge in distribution. Quite interesting. If all the degrees are at least 3, the graph will be connected with very high probability. In fact, the probability of this connection will be of the order 1 over n. Okay? So you can detect, this was just to give an example, I don't say very much about proofs, but just to give an example that you can study very clearly what the relation is between the precise degree structure, in this case the minimal degree, which plays a very important role, and the properties, even the global properties, that the graph has. And that will be one of the, sort of the running threads throughout my talk. All right. So just in the case of the generalized random graph, where we were very flexible to choose these weights, now we're very flexible to choose the degrees. And of course you may wonder, well, how am I going to choose those? Well, one example would of course be to take them all the same. So di is equal to r for every I in n. Now then n times r needs to be even, otherwise I'm in a bit of trouble, but just assume that that is true. And then you would be dealing with sort of a random regular graph. Well, not quite, of course, because in all the combinatorial models of random regular graphs, you take one random regular graph uniformly at random from the collection of all regular graphs. Now, in this case, we may actually get graphs that are not, according to the combinatorialist rules, random regular, in the sense that they may have some self-loops, and they may have some multiple edges. Okay? That's why I call this within quotations. There's actually a relation between the two models that immediately follows from the fact that you can explicitly compute, for a degree distribution, what the probability is of observing any graph. So here what I will be doing is I will be denoting my graph, which of course has vertex set n, but I'll just be writing it as a sequence of numbers xij, where 1 is less than or equal to I, less than or equal to j, less than or equal to n, and xij is just capital X's, because these are random variables, is just the number of edges between I and j. Okay? So if I know all of these x's, I know precisely what my graph is. Okay? And I also know precisely when the graph will be simple. That actually means that on my diagonal, the xii's, I should have all zeros, and my xij should all be less than or equal to 1. It's precisely equivalent to being simple. So if I describe my graph in the following way, my multigraph, I can explicitly compute the probability of observing any such graph. So here I have this little graph, G, which is denoted with these little x's. I, of course, choose my little x's in such a way that the degrees are precisely what they ought to be. And here you should bear in mind that I need to count a self-loop twice, which I do because the xii is counted once here and once there. So it really is doubly counted. Bear in mind that the self-loop eats up 2 half-edges, so it attributes 2 to the degree. Okay? So this is a given, because I know what my degrees are in my configuration model. I fix those. And then I can compute the probability of observing any specific multigraph. And that turns out to be the following thing. You get 1 over ln minus 1 double factorial. So this is for odd numbers, and you go down by 2, not by 1. In the factorial, you go down by 1. In a double factorial, you go down by 2. Then you have a product here of di factorial. You divide here through by the product over I 2 to the power xii. So that's the self-loops. And then you divide through by a product over all I and j of xij factorial. Okay? This is just the computation that you need to do. It's not very difficult. It's counting different configurations, meaning matchings of half-edges that will correspond to the same graph. That's it. Okay? That's, by the way, why this is called the configuration model. I think this stems from Bela Bolobash, who thinks about the matching as being a configuration, and somehow putting all of the matchings together with the vertices, you actually get the graph. So you have a configuration, which is the matching, and then you have the random graph that is presented by it. Now, why did I show this formula? I mean, it's a nice formula, but one of the things that you can notice is that if the xii's are all 0, this factor is absent. 2 to the power 0 is 1. If the xij's are all in between 0 and 1, this factor is also absent. Okay, so what does that imply? Then actually the answer of this G is not going to depend on the precise choice of xij's, at least for those possible x's for which you don't have self-loops nor multiple edges. Okay, let me repeat that. It basically means that if I don't have multiple edges and don't have self-loops, the probability of observing that graph is the same for all the simple graphs with the same degree distribution. Because then the right-hand side only depends on the d's and ln, which is the sum of the degrees. So that's the same thing as saying that if I condition on simplicity, actually all the simple graphs have the same distribution. But that's then the same thing as saying that conditionally on simplicity, my configuration model is a uniform random graph with that degree sequence. That's pretty nice. So I started out by doing this weird model that actually may produce self-loops and multiple edges. And then I created this sort of ambient space of multigraphs. But if I condition on being in the smaller set of simple graphs, I actually get a uniform simple graph with that degree distribution. Okay? Now, it may be that I'm conditioning on something which is terribly small when n tends to infinity. If that is the case, then we're in tough luck. Because then this is not going to work. Right? I mean, basically, this opens up the route of studying uniform random graphs with a given degree distribution by studying the configuration model. But if the probability of being simple is vanishingly small, extremely small, then this is going to be very difficult. And actually, that route becomes inaccessible. Now, as I'll explain a little bit later on, it turns out that the probability of being simple under reasonable assumptions is not that small. it actually remains strictly positive and converges under the assumptions that I was creating. That's pretty nice. So then it actually means that if I want to know how many graphs there are with a given degree distribution, well, if I look at this thing and condition on simplicity, then this number is always the same. So it must be equal to 1 over the total number. So I can invert and say that this number is the same as this object, where I crossed out those because the xi's were 0 and the xij's were in between 0 and 1, and I get this formula for the total number of graphs with the given degree distribution. So this is a completely combinatorial problem. Here I'm counting graphs with certain properties, and I'm transferring that into a simple factor, which is of course humongously big, but still it's a very simple factor, times a probability that a certain model that actually is not very difficult to write down actually produces a simple instance. And this actually has been the way in many cases to determine the asymptotics for the number of graphs with a given degree distribution. So this is I think, a very nice example. It's not my example, it's Bela Bolabash's and earlier people. It's a very nice example of a probabilistic method. You have a completely deterministic problem, you want to count something, you translate it into a probabilistic problem, you analyze the probabilistic problem. Of course, I haven't yet told you how you should analyze this thing, but we'll get to that. Any questions about this? Okay, then let's think about this simplicity probability. Oh no, I'm not doing that. I'm first going to discuss something else. When I started working on random graph theory, I was always amazed by people looking at sort of these inhomogeneous random graphs and then saying, okay, we'll go and study the configuration model, and then the results also apply to this inhomogeneous random graph, including even the Erdős and Rényi random graph. So there are papers who say, you know, we study something for the configuration model, and then actually we can lift it to the Erdős and Rényi random graph. Now, in some cases, the Erdős and Rényi random graph is actually more difficult than the configuration model. Let me give you an example. If I take the perspective of a uniform edge in the configuration model, this is very simple. I take a uniform half edge, I pair it. This gives me two vertices, and I know exactly every property that this edge has. This is a very simple thing that I can do. Now imagine doing the same thing for an Erdős and Rényi random graph. Okay, I have a binomial number of edges. I take one of them, and then I would like to see what my neighborhood looks like. For example, you know, of this edge, what are the degrees in the two endpoints? Well, you know, what is this edge? It's a uniform edge, but you know, choosing it actually reweighs the probabilities. So it's actually not so easy to study what the properties of these two degrees at either end of this edge would be. Whereas in the configuration model, that's trivial. So if we want to do this, you could say, first study it for the configuration model, and then I find a way to transfer those results to the Erdős and Rényi random graph. But then, of course, you need to know how to do that. And that's a non-trivial question. But let me explain how that works. This is related to a very similar uniformity statement that we were seeing here. Namely, here we were saying, conditionally on the configuration model producing a simple graph, the resulting random graph is uniform. For the generalized random graph, it will always be simple, so it's not going to be that conditioning, but it's a different conditioning that you have to do. And the conditioning that you have to do is that you have to condition in all of its degrees. Okay? So I have this generalized random graph with the edge probabilities that I've still written here. Now I condition on every degree in the graph. Conditionally on that very complicated event, the resulting graph turns out to be uniform at random from the collection of all graphs with the same degree structure. So in particular, it's the same as the configuration model conditioned on simplicity. That's a pretty nice connection. So how this is being used is that properties are being proved for the configuration model, then they're lifted to the setting where you condition on simplicity. Therefore, you get it for uniform random graphs with that degree distribution. And then for the generalized random graph, you say, okay, if I were to condition on the degrees, then it would have the same law. But of course, these degrees are random. Now, if in the configuration model I prove something under certain assumptions on the degrees, and if I can prove that those assumptions are actually going to be true, so bear in mind, we had these assumptions for the degrees. It's precisely this, these kind of things. So if these kind of things are going to be true for the random degree sequence of my generalized random graph, then actually I get the same results in the generalized random graph as I've proved for the configuration model. It's a pretty neat trick, okay? But it all bears on this property. So I'm giving a course, and I've asked beforehand, so how much should be divided in terms of proofs and in terms of sort of a high-level explanation. I think what I've done so far is more of a high-level explanation, so let's give a proof. I'm trying to give one proof for every lecture that I give. So this theorem notation, there's 1, 6, 15. That means that it's theorem 615 in volume 1. So later on, we'll see some theorems from volume 2. In fact, the numbering there is not entirely fixed yet, but then at least you know how to interpret these results. All right. So let me look at that proof. All right. So, proof. So bear in mind, I'm now conditioning on the degrees of all the vertices. Okay? And again, think of my graph as corresponding to my vertices and a collection X, where X is this Xij. 1 less than or equal to I, now strictly less than j because my graph is simple, less than or equal to n. And what I would like to show is that conditionally on the degrees being all fixed to some predefined sequence, actually the graph that I get is uniform amongst all sequences. So I'm just going to look at this, the probability of these, of observing a certain x. And bear in mind, these x's are Bernoulli variables. They're all independent. But now, of course, I'm conditioning on the degrees. So they're no longer Bernoulli. Okay? So what is the conditional distribution? Well, that's basically the following. I need to look at this collection being little x, and I need to condition on the degree of vertex I in my configuration x, which is this, to be equal to the predefined little di. Yeah? Now this is a conditional distribution, so this is clearly the same as the probability of this intersected with that, but I'm assuming that my x is such that this actually is true. So then I don't have to take the intersection. And then here I'm going to sum out over all, well, let me do it one step at a time. It's the probability that di x is equal to di for every I in n. So I've specified all the degrees to be little di. Now, of course, I can write that as a probability that x is x, divided by the sum over all the y's, which, bear in mind, are these sequences of zeros and ones, such that the di of y is equal to little di for every I. Is this readable, by the way, in the back? Yeah? Very good. Probability that x is equal to little y. Okay, so far so good. Now I have this formula. And I still need to compute this. And bear in mind that Pij is Wi Wj over Ln plus Wi Wj. That was my generalized random graph. And also bear in mind, because this will be important, that if I take 1 minus this, I'm just going to get ln divided by ln plus Wi Wj. Okay? Now here I'm no longer conditioning on the degree distribution. So here I can use that my indicators are independent. That's actually very nice. So what is this probability then? The probability that x is equal to x. Well, the little x actually specifies which Bernoulli indicators ought to be there and which Bernoulli indicators are not allowed to be there. Okay? So this is the product over all possible Bernoulli indicators of either Pij when the Xij is 1, or 1 minus Pij when the Xij is equal to 0. So a complicated way of writing this is Pij to the power Xij. That will actually be Pij when Xij is 1 and 1 otherwise. And then in a similar way I can write 1 minus Pij to the power 1 minus Xij. So this is just the same thing as Pij when Xij is 1, and it's 1 minus Pij when Xij is equal to 0, and that's precisely what it should be. All right. So far, so good. Here I've crucially used the independence, by the way. Okay. So I have not yet used this very specific edge probability, which will turn out to be crucial, and it will turn out to be crucial right now. So here I'm going to write this, and now I'm going to write Wi Wj divided by Ln plus Wi Wj to the power Xij. And then we get this Ln divided by Ln plus Wi Wj to the power 1 minus Xij. Okay? All right. It's actually useful to replace Wi over square root of Ln by Ui. Okay? Then actually what we see is that this product can be written as Ui Uj divided by 1 plus Ui Uj to the power Xij. And here we get 1 over 1 plus Ui Uj to the power 1 minus Xij. Okay? Now, actually, this factor is there for both of the terms. So I can bring it forward. That will just be a constant. This is going to be the product of 1 less than or equal to I less than or equal to j less than or equal to n of 1 plus Ui Uj to the power minus 1. That's actually killed this term and that term. And that's constant. I mean, it doesn't depend on the x's. This is the term that still depends on the x's. Okay? All right. So let's put big brackets around this and compute this. It's the product from I smaller than j less than or equal to n less than or equal to 1 Ui Uj to the power Xij. Now you should just count how often the different Ui's and the Uj's appear. And what you will see is that this latter term, this just remains. Actually, it's strictly less here, and here as well, and here as well. This is just a product over the vertices of Ui to the power di. Just count how often ui occurs. Well, it occurs for all the j's that are larger when xij is 1. And it also occurs here for I, for all of the other ones that are smaller, when xij is 1. So you get it once for every time when xij is 1. But the sum over j of xij is just a degree. So the ui appears precisely the sum of the xij summed over j times. But that's the same thing as a degree. Okay? So now what we've computed is that this probability here is actually a function of the degrees. And of the degrees only, not of the xij's. That means that this probability is the same for every choice of the x's that produce the same degrees. But then if I look at this one will be the same as that. So then this is actually going to be 1 over, well, the number of y for which diy is equal to di for every I in n. Well, that's the same thing as saying that your graph is uniform under that conditioning. And there we go. That was my claim to start out with. So now we've proved it. Now, this, of course, this trick has been used many times, for example, for the Erdős and Rényi random graph. But it really does explain how you should do it very carefully. Because, you know, the weights weren't exactly lambda. They were almost lambda, but not quite. You have to be a bit careful here. So you would expect some sort of similar independent or conditional uniformity to be true in other models, for example, the Chung and Liu model, but there it's not so obvious. I mean, the fact that this all worked actually all boils down to the fact that this ln plus wi wj that you have here is also present here. If that wouldn't be the case, this trick wouldn't have worked. So this is closely related to what are called likelihood ratios. And you really have to put it up this way in order to get this. All right. So why is this useful and how does this tie into my previous discussions? Because I've been building sort of this relatively abstract framework where you can get these degrees distributions that converge in distribution. Well, out of this you can understand why. Okay? So we have that conditionally on the degrees, this generalized random graph has the same distribution as CMND, conditioned on simplicity. Okay? Now suppose I want to use that as a way to prove properties for this generalized random graph. Then of course I never condition on the degrees. These degrees are going to be random variables. But I could consider it to be a functional of the random degrees. Bear in mind, these degrees are not going to be independent. They're almost independent, but not quite, right? So we should not be investigating always the configuration model with IID degrees. Then I would not be able to transfer the results. And this actually explains why we've been looking at sort of funny conditionings like this. These turn out to be the minimal requirements you need for many of the results to apply. You always need some sort of regularity. By the way, for the generalized random graph, that regularity is precisely this statement. So that we already have under the appropriate conditions. So that's actually pretty nice. If you then look at the other things, this will be the average degree. And you need that the average degree will converge to some constant. Okay, that may also be possible to prove. This one is typically the hardest. And it may not at all be obvious why we need these kind of things. So let me explain that next. Is this relation between generalized random graph, so Erdős and Rényi random graph, and the configuration model clear? Okay. So, I mean, you could summarize this whole thing by saying that there's two different reasons to study the configuration model. The first is that if you condition on simplicity, it's uniform. That's actually very nice. So that allows you to prove all sorts of properties of uniform random graphs, including their numbers. So that's one application. The second application is that it allows you to study a certain class of inhomogeneous random graphs because you can somehow link the two by an appropriate conditioning. That's a second reason to study the configuration model. Okay? However, in all of these analyses, we've still assumed that the degree distribution is nice and that we can condition on simplicity. This conditioning on simplicity is, of course, a bit of a problem. So let's discuss that next. And that's where we'll see the second moment appearing. Unless there's any questions at this point. All right. Okay. So we're interested in simplicity. Simplicity is the same thing as saying that there are no self-loops nor multiple edges. So no two cycles nor self-loops. Okay? Now it's here that the second moment assumption kicks in. In fact, under the second moment assumption, you can show that the number of self-loops converges to a Poisson random variable. Now we know that sums of independent indicators with very small success probabilities, such that the mean converges, they're very close to Poisson distributions. But there's a lot of tricks that allow you to deduce Poissonian asymptotics for all sorts of other settings, including settings where the indicators that you're thinking about are actually dependent, as long as they're weakly dependent. There are several ways how you can do this. Okay? So let's do a very simple arithmetic for counting the expected number of self-loops. Okay? The expected number of self-loops. Sn is the number of self-loops. And a very similar arithmetic can be done if you're interested in the number of multiple edges. So let's just stick to self-loops for the time being. Okay, well, that's just the same thing as the sum over I, the expected number of self-loops at I. Okay? Now, that's equal to 1/2 the sum over I in n. The sum from S is 1 to di, the probability that S creates a self-loop. So the 1/2 comes in because there's symmetry. Right? I shouldn't count the self-loop between, let's say, 1 and 5, and then between 5 and 1, because they're the same self-loop, if 1 and 5 correspond to the labels of the half edges. But I can count them both if I divide through by 1/2. And in expectations are linear, so I can do that. That actually explains the 1/2 here. Okay? Very good. So that's one step to go. And now we're going to be using the very nice property of the configuration model, because what I said was that the order of attaching the half edges doesn't matter. So I might as well think of this S half edge as being the very first one that I'm attaching, that I'm pairing. And then I'm looking at the probability of creating a self-loop. Well, then it better attach to one of the di minus 1 other half edges incident to I. And that occurs with probability 1 over ln minus 1, because you pair things uniformly at random. So what do I get? I get di minus 1 divided by ln minus 1. Well, that doesn't depend on S. So I might as well rub that out and multiply that simply by di. Now, and in terms of the capital Dn, which is the degree of a uniformly chosen vertex, this is nothing but the expectation of dn times dn minus 1 divided by the expectation of dn. And it's here that we see that this second moment enters. So under this assumption C, the condition C that says that the second moment also converges, this will actually converge to 1/2 times the expected value of d times d minus 1 divided by the expected value of d. So what do I have? I have an object that I can write as a sum of lots of indicators. They all have very small probabilities of success, because even if I sum them out, I still get something which remains bounded. So I have lots of very minorly dependent indicators whose average will converge. Well, then there are lots of tools to actually show that the random variable itself also converges to the same thing it would have if the indicators would have been independent, which is Poisson. So indeed, under this assumption, it follows, now of course you have to do more work here, that actually Sn converges in distribution to a Poisson random variable with that parameter, which I will call nu. So this is nu. And this will come about in later lectures. Okay? Now bear in mind that a Poisson random variable has a positive probability of being 0. So what we get out of this is that there is a positive probability of not having any self-loops. That's good, then we're already halfway towards simplicity. Now you can do a very similar analysis on the number of multiple edges. I will not do that because we're running out of time. So this is the number of edges that are between two vertices that are multiple. So if I have 1, I just keep that 1. If I have 2, I count 1. If I have 3, I count 2. So it's sort of the excess number of edges that I would have to remove in order to make the graph simple or not having any multiple edges, right? And this turns out to converge in distribution to a Poisson random variable, and I always have to think about that, nu squared over 4. So the 1/2 here came from symmetry, and the 1/4 here also comes from symmetry. It's a very similar idea. And actually what you have to do is somehow count I here, count j here, and look at two, a pair here and a pair there, that are connected to each other. Something like that. And the probability for that to occur is somehow related again to this nu, but actually you get two, one from I and one from j, somehow. Okay, I'm not explaining things very precisely. If you want to know it in more detail, look up the theory. It's actually not very difficult to make this stick and even get that these two limiting variables, that actually Sn and Mn jointly converge in distribution to two independent. Poisson 1, nu over 2, Poisson 2, nu squared over 4. And these are independent, the Poisson random variables. So that in particular implies that the probability for simplicity, that's just going to be the same thing as the probability that Sn and Mn are both 0, which is going to be the probability that these Poissonians are going to be 0, which is just e to the power minus the parameters. So the probability that Cmnd is simple converges to e to the power minus nu over 2 minus nu squared over 4, which is the same thing as the probability that these two both are equal to 0 by independence. This is strictly positive under my second moment assumption. So that means that my configuration model will be simple with positive probability. Now that's a very nice property because it immediately implies that if I prove any convergence improbability for the configuration model, the same property will hold, again in probability, for the configuration model conditioned on simplicity. Somehow conditioning on a positive measure event is not going to change convergence in probability. Everybody know what convergence in probability is? think about convergence in distribution to a constant. That's typically the kind of cases that we'll be looking at. Okay? So this immediately offers the route of proving stuff for uniform random graphs if we can prove them for the configuration model. Okay? That's actually somewhat surprising because if n tends to infinity, on the one hand, there are many more possibilities of actually creating self-loops at the various vertices. On the other hand, the probability of doing it decreases because there are many more half-edges out there and you need to do something pretty unusual. And somehow this balances out in such a way that on average you see a fixed number. And this explains why the large n limit of the probability of simplicity is a positive number. Now when tau is in between 2 and 3, recall tau was the power law exponent of the degree distribution, then actually this new parameter is infinity. It's not very hard to show that indeed this convergence then also holds, except that the right-hand side is 0. If only because you're bound to have self-loops. Because if tau is in between 2 and 3, then you're going to have very large degrees, and therefore it's actually pretty likely that you're going to create self-loops. So then, all bets are off. Because conditioning on simplicity becomes very hard. I don't know how to do it. So there's probably not the best way of studying random graphs with that setting. Now, there are other techniques as well to studying random graphs with given degree distributions, such as switching identities, etc., etc. But that's not what I'm going to go after. In fact, I'm just perfectly happy to study the configuration model and ignore self-loops and multiple edges. For example, by studying the erased configuration model. In the erased configuration model, what you do is you just remove all the self-loops and you glue all the multiple edges together. That will give you a simple graph. Okay? It doesn't quite have the exact same degree distribution because you've removed a few of the edges, but still you're removing very little, even in the case when tau is in between 2 and 3. All right. I think I'm done with what I wanted to say about the configuration model. There's a few more minutes left, which I will not be using up, but I'll just show you what we're going to be doing on Wednesday. So on Wednesday, we're going to look at one more random graph model, which is actually quite interesting. Because, it's a preferential attachment model. And one of the things that is maybe not so nice about the configuration model and the generalized random graph is that they will have power laws if we stick them in. We really have to put in the power laws by hand ourselves, either by making the weights obey a power law or by making the degrees obey a power law. Now that's of course very nice, and it will be a wonderful way of modeling any static network model that has a power law, but it's not going to tell you anything about why these power laws might occur. Preferential attachment model approaches this completely differently. It's a dynamical model. And the dynamics is very simple. I'll explain all about the dynamics on Wednesday. But at a very high level, the dynamics is such that vertices that have a high degree are more likely to attract edges of vertices that come in later on. And this actually gives a preference. That's why it's called the preferential attachment model, or sometimes also the rich get richer model. And this preference makes sure that vertices that have a high degree are more likely to become even larger, and that increases and boosts their degrees. And it actually turns out if you choose your parameters in your model in the right way, it boosts it in such a way that the graph that you're going to be obtaining will have a power law. And bear in mind, now we did not put the power law in. We've proposed a dynamics that maybe is reasonable. Social dynamics, people who are more active are more likely to get to know newcomers in town, right? There's some preference there. We've put that into a very simple microscopic rule, and that microscopic rule is then such that in the end we're going to have power laws. So it offers more of an explanation of why we see power laws. Of course, the question is whether you believe that explanation, and there's much that can be said about that, and I will certainly do that on Wednesday. but it certainly is an intriguing idea. All right, my time is up. Thank you very much for your attention.